Right. So good morning, everyone, once again. So today we are going to start the last topic, multiprocessors. So far we've been talking about memory systems and caching. Then we went on to talk about virtual memory also. Now we are going to talk about multiprocessor systems, and this has again a lot to do with memory. So let's start with a quick recap about performance aspects of processor systems, which we have been talking from the very beginning. So if you remember, um, from the very beginning, from the very first class, we started talking about performance of computer systems. And at that time, we defined things like cycle time, CPI, that is cycles per instruction, and how the clock frequency of computer processors changed in the past few decades. Right? So we discussed about different clock frequencies, and at around 4 gigahertz, there was a problem that the engineers encountered, so that they couldn't keep increasing the clock frequency, and that problem we referred to as the power war, as they kept increasing the power, increasing the clock frequency, that is reducing the clock cycle time. At a certain point, they realized that the power dissipation or power consumption became too high, such that the chip became overheated. We couldn't cool the chip fast enough to keep it running at a healthy temperature. So yeah, reducing the clock frequency was one of the primary methods of trying to improve performance of a processor system, increasing the clock frequency or reducing the clock cycle time. So idea is you spend less time on processing instructions. So then, because of this reason, a different concept came into the picture, that is instruction level parallelism. How do we process multiple instructions in parallel? One of the main technologies that was involved in this, or main concepts that was involved in this, was pipeline. And then with that came the concept of throughput to define perform. How many instructions can you complete in a given time, right? So pipelining allowed processors to say keep working on multiple instructions at the same time by utilizing the different hardware at the same time. While you process or say do the execution work of a certain instruction, you can do the register access, accessing the data of another instruction and fetching another instruction, right? So that was the pipelining concept, which allowed us to exploit certain degrees of parallelism inherent in computer programs. Then even though we didn't discuss detail in the class, I gave you some external references, extra reading. There are some advanced concepts like multiple issue, out of order execution, right? So different advanced techniques to further exploit parallelism. What instructions can we execute when there is a stall in a pipeline? If there is going to be a stall in the pipeline, can you maybe execute some other instruction to make use of the hardware during that time, right? So different techniques. So all these techniques try to exploit more and more parallelism available in program. Then you come across another problem where programs only contain certain degrees of parallelism. Inherently, you can only execute a number of instructions in parallel. You can't go beyond that. There are the dependencies that prevent you from doing it. So you come across a parallelism wall, so to speak, right? So while this is happening, we know what Moore's law is, right? So that is, it's not a law per se, but it's just a prediction, a guideline saying the number of transistors available in the standard computer processor chip doubles every year. So every 2 years or so. So yeah, so the technology, underlying technology, it keep improving by different means. So you get more and more transistors, but how do we use them? You can't keep increasing the clock frequency. You are going to have heating problems, power problems, and you can't try to execute multiple instructions from a program more than a certain limit, because the inherent parallelism in a program is limited. It depends on the program, but it's usually limited. So then how do you use these extra or abundant transistors available on chips as we keep improving underlying technology? So the intuitive approach to go ahead with this is using multiple processors, putting multiple processor cores on the same chip, which can process multiple streams of instructions, or rather multiple programs at the same time. So the striking difference is, in a single processor system, no matter what sort of an illusion you get from a user's perspective that hundreds of programs are running at the same time, if there is only one processor, the real execution happens in a sequential manner, bar any instruction level parallelism exploited using techniques like pipeline. But in multiple processors, multiprocessor systems, you actually have several cores, several processor cores working at the same time. So you're executing several sequences of instructions at the same time. So you're executing multiple threads or multiple programs running at the same time simultaneously in real time, right? So in such systems, we are going to talk about such systems and architectures under this topic. In such systems, the processors are usually referred to as PEs, or processing elements. It's one of the common terms used. There are other terms used to describe processing elements, but PE is a very common term used in this context. Then one of the key problems that engineers have to address in multiprocessor systems, when designing multiprocessor systems, is the communication between these processors. Now, you have multiple hardware processors executing multiple sequences of instructions at the same time. So if these instruction sequences or programs are mutually exclusive, if they are not related at all, there may not be a big issue. But usually, if you try to get your overall workload done as quickly as possible, then you try to split your program into several threads and they have to communicate. So communication between processors in multiprocessor systems is one of the key problems that engineers have to address, and that is what we are going to focus on under this topic. Right. So when dealing with this multiprocessor communication problem, the most common method we use is sharing memory between multiple processors. Right. So whatever the communication that processors need to do between them, among them, has to happen through shared memory. And that is one of the most intuitive approaches that engineers can take when designing multiprocessor systems. So shared memory multiprocessors are very, very common, and we'll talk a lot about that in the coming few slides. So SMMs, for sure, shared memory multiprocessors. So as you can see in this picture, you have 3 processing elements, right? So multiple processing elements. Each processing element is a processor, basically a CPU. like we have learned in one of the previous chapters or topics in this course, right? So you will have instruction fetching, decoding, execution, all those things in a single processing element. It's a CPU basically. So you can see that they are connected through a bus, a common interconnect. All these three processes, PE1, PE2, PE3, they are connected to a bus. And a memory device is also connected to the bus. And by definition of these shared memory multiprocessors, the available memory and address space is shared between the processors in the system, right? So when memory is shared between processors, there should be some mechanism to manage how memory is shared, right? So when you're writing or reading from shared memory, there should be some sort of arbitration, and that is done by the operating system. So which processor can access which portion of memory, is that memory portion shared, is that memory portion private, all those things are handled by the operating system. And as you know, operating system again itself is a program. So that is also in the memory. The code for the operating system is also in the memory. And since the memory is shared, the operating system is also shared. So any operating system code executed by these processors are shared. They're coming from the shared memory, and any processor can execute the instructions from the operating system code as well. Right. So the physical address space, like I said earlier, is shared among all these processing elements, and the operating system needs to perform some sort of a workload balancing among these processing elements in general to get better utilization, right? So there is no benefit, no real benefit to us if only one processor is running all the work and the other processors are idling or doing very little work, right? So you need to balance the workload. All the processors should be working in parallel at the same time, sharing the workload of the overall task to be executed, to be done, right? So workload balancing is done by the operating system. So there should be some sort of software mechanism in the operating system design itself to handle to balance the workload among the available processing elements. So if we didn't have the shared memory concept, just to give you the contrast, if we didn't have the shared memory concept, then the processing elements can have their own memories, and in those private memories, there will be the operating system code will be there. So those operating system codes are private to each individual processing element. So operating system is not shared. When the operating system is not shared, then sharing of memory to communicate cannot basically be done, right? So you need some other mechanisms. We will also talk about that after we talk about shared memory multiprocessors. So by the definition of shared memory multiprocessors, we have the operating system in the shared memory. So it is also shared between processors. It's a program, it's shared between processors. Right. So when a memory device and address space is shared between multiple processing elements, we come across an inherent issue here. Memory contention. All these processing elements are trying to access the same memory device, right? So you can imagine now in the lab, you're developing your processor CPU, single cycle CPU to access memory, right? So synchronizing between these memory accesses, how the processor can request the memory to perform an operation, and the busy waiting and all those things, it takes a lot of effort to synchronize properly. And it takes a lot of time to access memory, as you are finding out, right? So now we have multiple CPUs, multiple processing elements accessing the same memory. So they have to contend to gain access to the memory, right? So if one processor is already sending a request to memory to do a read, then the other two processors, they have to wait. So more waiting time, right? And the traffic on the bus is now more. We have a lot more read and write requests going through the bus because all these processors are sending read and write requests. So the bus is going to be very busy, and the memory, the processors are going to contend to access memory. There's going to be a competition to access memory. One say when all these processors are trying to access the memory at the same time. So that is one of the biggest problems that we encounter in shared memory multiprocessor systems. Then, based on how each CPU sees the memory, how each CPU sees the memory. So from the perspective of the CPU of the memory, right? So based on that perspective, there are two definitions, two classes. We classify multiprocessor systems into two classes. One is uniform memory access. The other one is non-uniform memory access. Uniform memory access is usually referred to in short as UMA, and non-uniform memory access, NUMA. So uniform memory access means each processor sees the memory in the exact same way. So these processors share the address space. So address space they perceive in the very same way, but the time spent on accessing any given memory location should be the same for each CPU, assuming that the bus is not blocking, that if you can ignore the contention. Other than that, by the design, there is no difference in the average time spent on accessing any given memory location for any CPU. That is the feature of uniform memory access. Non-uniform memory access systems, in contrast, is different. Right? So we will have a look at those two now. So in uniform memory access, as I told you, all processing elements experience the same average memory access time, independent of the PE. So the time spent, average time expected to be spent on a memory access isn't dependent on individual processing elements, right? So the shared memory appears in the same way to all three processors in this particular example, any number of processors available in the system, right, in general. So such UMA systems are all also referred to as symmetric multiprocessors, SMPs. Both these terms are used to refer to the same type of system, uniform memory access system. Right. Now, processing elements, like I told you earlier, have to wait for the bus to be available when they need to access memory. Whenever they need to access memory, they need the bus to be available, because bus is the interconnect connecting all these processors to the memory. Right? So if one processing element is already using the memory, then the other processing elements will have to wait until that access is finished. If processor PE1 is accessing memory right now, it will take a large number of cycles, right? So hundreds of cycles. Other processing elements will have to wait until PE1 completes its access, right? So bus is going to become the bottleneck because of the memory contention. How can we avoid this bottleneck? Can you suggest a solution from what you have already learned? We can use caches, right? We can use cache memories to address this bottleneck. Just like we use caches in the normal uniprocessor, single processor systems, we can use caches to address this bottleneck issue. You have local caches for individual processor. P1 can have its own cache, P2 can have its own cache, P3 can have its own cache, right? So as we discussed when we learned about caches, the idea is based on the locality available in computer programs, we can serve most of the memory accesses at the cache itself, and only for a very small percentage of accesses when you have a miss, when you don't have the data available in the cache, you have to go to the memory, right? So that is the core idea of caching, exploiting temporal and spatial locality available in computer programs. So we can use the same concept and have local caches, private caches for each processing element, right? So when we do that, what happens when a shared data block is fetched into separate local caches? Imagine there is a block of data, right? A block of data in memory, and that block is shared between all these programs, all these programs, the programs running on these processing elements, all of them need to access that block at some different times in the execution timeline, right? So at some point in execution, PE1 will request access to that block, and that block will be fetched into PE1's cache. And the same can happen with PE2 and PE3. The same block may be fetched into all these different caches. Can you see a problem that can happen when such a shared data block is fetched into multiple different caches? Can anyone point out an issue that might happen with this setup? A shared block fetched into multiple caches. Can you see a problem? Yes, exactly. Some processors might not use the most recent data, right? So now these processing elements of programs running on these CPUs, they read and write to those data, right? Both. So when one program writes, the data in that particular cache will be updated, and if the system is write through, if we use a write through write policy, then that data will be written to the memory as well. But if the same block is already in another cache, that cache has old data, stale data, right? Not the most up-to-date version of that particular piece of data. So when that processing element tries to read the data, that processing element will access all data, and it will not know any better that there has already been an update to the same data block. So let's take an example. Right? So this is called the cache coherence problem. So let's take an example. Assume there is a variable in memory, x, right? Programs will refer to that as x, and the value of that variable is 1, right? And that will be part of a data block in memory, right? So this x variable is accessed by the programs running on all these different CPUs. Let's take an example sequence of operation. So processing element 1, P1, now reads X. At this point in time, PE1, the program running in on PE1, reads the value of X. And since X was not initially available, since this is the first time PE1 reads X, it's not in the cache. And that cache then goes to the memory and fetches the block containing that data word. Now, the data block containing that word is in the cache of PE1, right? So X equal 1 is in PE1's cache. The value is 1. The value of the variable X as seen by processing element 1 is 1. Okay. Now, processing element 2 also reads the same address, same value, right? So same address in the memory, fetches the cache, fetches that into itself and store it. So now both these caches have the same memory address cached, and the value is 1, and the value in the memory is also 1, so it's fine, right? The same value is there. So a future read in any one of these two processes, they will get the correct up-to-date value. Now, now one of the processes, P1, is going to perform a write operation on the same memory address. P1 writes X equals 0, right? So X was 1 to begin with. X equals 0 was written by processing element 1. The program running here performs a write to that memory address X. The value, new value is 0. So we write, the cache gets the update, X equals 0. That memory, the value in that memory word, the data word here is set to 0. It was a hit here in the cache, right? Because the cache block was already there. It's a hit, and that block was updated to be 0. The value was 0. And if we can assume the write policy is write back, then memory will not get updated at this point in time, right? Write back write policy says this block will only be written back to the memory when the block is evicted from the cache, thrown out from the cache, right? So at this point in time, we are not going to perform the write to the memory. Memory will have the old value, right? So there is now we have the inconsistency between the cached value and the memory value, right? So at this point in time, processing element 1 sees the value at memory address X as 0. Processing element 2 sees the value at same memory address as 1, right? So now they are seeing the same value at same address with two different values. That is a problem, right? Now there's an inconsistency, incoherence between the way these two processing elements sees the memory address, the value at that memory address. They are not seeing the same thing, right? So the value we say is incoherent. Now, what happens if the write policy was write through? When P1 writes X equals 0, that write will happen in the cache as well as the memory, right? The cache will write to the memory. So both cache and memory will have the up-to-date value, but the caches in other processing elements will still have the old value, right? Stale, incorrect values. So now still again, we have the caches are not coherent now. The processors don't see the same value for the same address. We say the coherence among caches is lost. We are not seeing the same thing in these different caches. Same address, different value. Same address, different value. So cache coherence is lost. So in order for us to run parallel programs, communicating programs on a multiprocessor system, cache coherence must be maintained. Otherwise, the programs will not execute in the way we expect them to be executed, right? So we will get incorrect results. the latest updates are not being seen by these other processors because they have old data cached. So we have to address this problem. Cache coherence must be maintained, right? We can't let caches to be incoherent, contain incoherent data if we want to perform parallel processing with communicating programs, right? So the coherence, maintaining of coherence is usually handled by the cache controller. So there are different techniques and protocols we can use to maintain cache coherence in a multiprocessor system among these multiprocessor caches. So we will have a look at some of the very common approaches. So one of the basic approaches we can use to perform cache coherence or maintain cache coherence rather is called bus snooping, right? So it's a technique used in SMP, so symmetric multiprocessors, uniform memory access, right? So we are still talking about UMA systems, symmetric multiprocessors, and to address the cache coherence issue, bus snooping is one of the most common techniques used. Let's see what this is. So in bus snooping, what we do is we have another separate dedicated bus called the snoop bus, which is used to control coherency among data, cache data, right? Data in these multiprocessor caches. So snoop bus is, the sole purpose of the snoop bus is to control the coherency of the data in these multiprocessor caches. So in this bus snooping systems, whenever there is a write access, cache controllers share the address through the snoop bus, right? So whenever, say for example, in our previous example, processing element 1 performed a write to memory address X, right? So whenever such a write happens, in addition to the usual memory operations that happen, write policy, whatever that is going on in the memory subsystem, in addition to that, cache controller share the information through the snoop bus, share that information with these other caches, the controllers of these other caches in the system, right? So this processing element 1's cache will say, okay, I received a write to memory address X. That information is shared or broadcasted to these other caches. And all of these caches are listening to the snoop bus to see if such a broadcast of information is done by other caches. So when the controller of, say, this cache, processing element 2's cache, sees that, okay, there has been a write done to memory address X by a different processor, right? That information is received by the cache controller of processing element 2. So what this cache controller has to do is listen to that, check if I also have that same address cache. Do I have that same address in my storage as well? If I do, then I need to do something about it, right? So that is the key characteristic of bus snooping system. So whenever a cache receives a write to any address, that information is shared through the snoop bus with other cache controllers. Other cache controllers seeing this information checks their own storages to see if we also have the same address cached. If we do, then we need to do something about it. And this something can take different approaches. So one way, or one of the most common ways rather, is to invalidate our own copy. If we have a copy of the data when some other processor performs a write, then what we can do is we can invalidate our own copy. That approach is called write invalidate, right? It's called the write invalidate protocol, rather group of protocols, right? So there can be other variations, right? Other differences. So you can define a group of protocols as write invalidate. So the key idea there is when you're listening to the Snoop bus, if you see that you have a copy of data which is now being updated by some other processor, then what you're doing is you're invalidating your own copy. How do you invalidate your copy? That is what the valid bit is for, right? Remember when we discussed in the previous topic, when we discussed what the valid bit is used for, the use was only at the very beginning of the execution, right? At the very beginning, when the cache is empty, all the blocks are invalid. When you fetch a block into a cache slot, that we mark that block as valid, right? So now we have an additional purpose for that valid bit in the cache. Now, what we can use the same valid bit to mark a block as invalid when a different processor performs a write to the same address. So when we mark the block as invalid, the next access to the same block is going to be a miss, right? So if we go back to the previous slide, the example, the cache coherence example, the issue was we had different values for the same address in these two different caches. Now, when processing element 1 performed the write, x equals 0, if there was a Snoop bus, processing element 2's cache controller will listen to that write broadcasted through the Snoop bus, and since it also has the same address in its storage, cache controller can now mark this particular block as invalid. So whenever processing element 2 tries to read the value of x after that, it will see the entry is invalid. So it needs to go to the memory and fetch the missing data. So if the memory is kept up to date, that is fine. Or else it needs to go and ask the other cache, right? So you can have different approaches to find the missing data, but the key idea is you mark the block as invalid, so you won't read incorrect data, right? So that was the problem, reading incorrect data. So we can avoid that problem by using a write invalidate type protocol. Invalidate your own copy if somebody else performs an update to the same address. Okay. Right. Now, next access, of course, is going to be a miss in the cache where that invalidate happened. But that is fine. We can go and find the missing piece of data. That is fine. We only need to spend some more clock cycles, but the correct behavior, correct functionality is now maintained. So when the write policy of the system is write through, memory is going to have the up-to-date copy, right? So like we saw in the previous slide, if the write policy goes write through, memory is going to have the up-to-date copy. So you can fetch the missing data block from the memory itself. If the write policy was write back, then memory is also going to have the old value, the stale value. Only the cache of the processor that performed the latest write is going to have the up-to-date value, right? So in such a scenario, what the other cache controllers can do is, if they are going to invalidate a particular cache block and going to suffer a miss in the future, they can go and fetch the missing data block from other caches using the Snoop bus. Snoop bus can also be used for that purpose as well, right? So there is a cached block here, but it is marked as invalid. PE2, we have a cache block, but it is marked as invalid. Then what we will have to do is to perform a snoop read, and other cache controllers, whoever has a valid data block with the same address, can provide the up-to-date data, right? So if we go back to the previous slide here, in this case, this is the write-through example. If the write policy was write back, only P1's cache is going to have the up-to-date value, memory is going to have the old value, right? So in the case of write invalidate protocol, when PE1 writes to X, the value 0, when this happens, that write is broadcasted through the snoop bus to other processes, and PE2 will see that, okay, not PE2 actually, the cache controller of PE2 here in this cache, it will see, okay, I also have the same block in my cache, so I am going to mark that block as invalid. Fine, that invalid bit is going to be cleared now. Next time processing element 2 is going to read the value of X, cache controller will see that there is the tag is matching, the address tag is matching, but the invalid bit, the valid bit is clear, it's not valid. So what it can do is do a snoop read, place a snoop read access on the snoop bus. So other cache controllers listening to the snoop bus will see there is a snoop read access coming now. So processing element 3 will see, it will also listen to that snoop read access, and it will see, okay, I don't have that block in my cache. So it will ignore that read request. Processing element 1's cache controller will see, okay, there is a snoop read request coming, and I have that block cached, then it is valid. So I have the most up-to-date value. So it can service that snoop read request. The value can be provided through this cache controller to the other cache controller, right? So it's actually more convenient than going to the memory. Memory, we know it's a slow process. You are going to spend a lot of clock cycles trying to access memory. So rather than doing that, using the snoop bus to access other caches to find the missing data, it's going to be more efficient. So in the write back caching, write policy, the cache controllers suffering the miss can snoop in other caches to find the most recent copy. Right? Place a snoop read request on the snoop bus, and the cache controller which has the most up-to-date copy, most recent copy, can supply the data. Right? So comparing to the write through caching method with the bus snooping technique, the snooping itself is now more complex, right? Earlier, you only needed to broadcast the invalidate signal whenever the cache controller receives a write to an address. Now, we have to have the functionality to read from other caches through the snoop bus as well. So your cache controller is going to be more complex, and the snoop bus is going to have more traffic, right? So you're going to have more traffic on the snoop bus. You're going to have to supply data on the snoop bus as well as those invalidation addresses, right? So your snoop bus hardware is going to be now increased. You need more width on the bus to accommodate data as well as addresses, and more control signals going through the snoop bus as well. The cache control is going to be more complex compared to the write through method, but less memory traffic, less time spent on memory, right? Up-to-date data can be quickly fetched from other caches rather than going to the memory. So overall, it's going to be more efficient. It's going to need more hardware, right? More power and all that, but processing, the performance is going to be better compared to write through. Okay. Then the other type of protocols are called write update protocol. Remember that I said cache controllers are listening to the Snoop bus to see if a broadcast write is coming, right? If some other cache controller is going to broadcast a write, if I also have the same data, same address in my cache, then I need to do something about it. And that something, one thing, the easiest thing we can do is invalidate our own copy. That was the write invalidation set of protocols. Other thing we can do is update our own copy. Instead of invalidating, we update our own copy. So that approach is called write update. The protocols using that update, that method, that technique is called write update protocol. Sometimes they are also called write broadcast, right? So in such systems, what happens is at every write access, the cache controller share the addresses, cache controllers share the addresses to the Snoop bus as well as the data, right? Cache controllers need to share address plus data, both in the Snoop bus. So other cache controllers which might have the same block cache can update their own copy. If you want to update your own copy, you need the data, right? Up-to-date data. So the new value is immediately broadcasted through the Snoop bus, right? So the benefit of doing this is the cache controllers updating their own data are not going to suffer a miss in the next access to the same block. If processing element 2 in our previous example is going to access the same data, same address, the data here will already have been updated and still marked as valid, because when PE1 wrote to the address X, the value 0, cache controller there has already broadcasted X equals 0 through the Snoop bus to the other cache controllers. So other cache controllers looking at that broadcasted write will see processing element 3 here. It will see, okay, I don't have that block cached, so ignore it. P2's cache here. Okay, I have that block cache, so I update the value X equals 0 and keep that block valid. So next time PE2 accesses the address X, it will see the up-to-date value X equals 0, right? It's not going to suffer a cache miss. So the cache controller becomes rather simple in write update type protocols, rather than having to perform an extra read access from other caches. You always receive the up-to-date data. You just update your own cache copy and keep it valid, right? So cache controller becomes rather simple, but Snoop bus is going to have these extra bus lines, right? Extra bus lines to supply the data as well as address. So you're going to have more hardware on the Snoop bus that is going to consume more power, but cache control is going to be slightly more simple than write invalidate protocols using write back policy, right? So, and the benefit is the cache is going to suffer less cache misses. You don't need to go to the memory as often, right? So that is the overall classes of protocols using the bus snooping technique to maintain cache coherence. Right. So this table here, this presents a summary of these protocols actually used in real systems. Right? So these are historic. This has a historic perspective of it. So we are looking at a certain set of protocols. Write once, Synapse N+1, Berkeley, Illinois, Firefly, and MESI or MESI for short. So, so if you take write once protocol, it's a name given to that protocol. It uses the write invalidate approach, right? Write invalidate approach, and the write policy in the system is write back after the first write. The first write is write through. After that, every write is going to be write back. So that is the feature of write once protocol, and it's one of the first protocols developed to use bus snooping to maintain cache coherency. And these are very old implementations. So Synapse N+1 is also a write invalidate type protocol, again using write back type policy in the system, and it's one of the first implemented cache coherency maintaining protocols in symmetric multiprocessors. Then the Berkeley protocol, it's also write invalidate and write back, used in Berkeley's per processor architecture. Illinois protocol, write invalidate, again write back. You're seeing that most of these protocols are write invalidate and uses the write back write policy for the entire system, right? So Illinois protocol was used in this SGI companies processors called Power and Challenge, SGI Silicon Graphics, if you may have heard about it. So these are again somewhere, I can't remember, somewhere in the 90s or late 80s. There were multiprocessor architectures developed for high performance systems called, one of the processors was called Power and the other one was called Challenge. Those processor architectures used the Illinois protocol to maintain cache coherence. One thing to note is these multiprocessors were first, the concept was first used in high performance supercomputer type processor systems. Right? So only later on they became more prevalent in normal personal computer systems, but they were initially developed in this large scale high performance system. Right. Then the Firefly protocol is actually write update, the only write update protocol in our group here. And it was used in the Spark Center 2000 architecture. It had a mixed write policy, write back for private data, write through for shared data. So there are two types of data. One type are private, only the local processor accesses those data. The other type are shared data where other processors might access as well. So they are write through and private data are write back for performance reasons. Then performance and functionality reasons. Then MESI protocol is a write invalidate protocol and uses write back policy, and it's used in these popularly known Intel Pentium processors, developed again. That was again in the 90s and early 2000s, and IBM PowerPC processors, which were developed by an alliance of IBM, Apple, and Motorola in the same age, same era. So those very popular client CPUs or personal computer CPUs use the MESI cache coherency protocol. And you can see that most of these are invalidate because they are very easy to implement. The overhead is less, and if most of these use write back protocol because it reduces the amount of memory accesses that we have to do. Memory accesses are very expensive in terms of performance time. So yeah, we like to do less memory accesses as possible. So write invalidate coherency protocol type and write back write policy are usually a very popular combo in multiprocessor systems. So next, we are going to look at this MESI protocol in detail because that's one of the most commonly used, most popular protocols So we are going to look at that in detail. We are not going to talk about the others in detail. Others are there for comparison and historic purposes. Messy protocol, we are going to take a closer look at. Right, now, in the Messy protocol, a block in a cache can have one of 4 states, right? We define 4 states, a state for any given block in the cache, right? So when you look at a cache block, you have valid bit tag and all those associated with the block. Now we are talking about state as well, right? So the state can be invalid, shared, exclusive, or modified. So you need 2 bits to represent that rather than the single invalid bit, right? So invalid, shared, exclusive, and modified. So what are these states? What are the meanings of these states? Invalid, as the name suggests, data is not valid, right? So if a block in a cache is marked invalid, then that data is not valid. The processor can't use that data. If the state is shared, that means multiple caches have copies of this same block, right? And the value is consistent with the memory. So imagine a particular cache, and inside that cache, a block is marked shared. So by looking at that state, the cache controller will know other caches are already at this moment, other caches have copies of the same block, and the value is the same as mine, and the memory also have the same value. Value is consistent across the board. In all caches and the memory, we have the same value, right? So then in that case, the state is marked as shared. Exclusive, on the other hand, is only cached copy, consistent with the memory, right? So if in a particular cache, there is a block marked exclusive, that means other caches do not have this copy at this point in time. Only this cache has a cached copy. Memory has the same value. The value in the cache block here is the same as the memory. If that is the case, the state is called exclusive. Then the final or 4th state is modified. Modified blocks are only cache copies. Other caches do not have this block, and the value is inconsistent with the memory. Memory does not have the up-to-date value. The up-to-date value, the most recent value, is in this cache, right? So if a particular cache controller sees a block in its storage that is marked as modified, that means that is the most recent, the up-to-date value. And even the memory does not have the up-to-date value. And other caches don't have a copy of this block. They don't have copy of this block. Valid or invalid, they don't have a copy of this block, right? Okay, so these are the 4 states defined in the Messy protocol. Let's take an example and see how these states transitions can happen. Okay, so for our example, we'll use the same system as previous, the same example as previously we took. So we have 3 processing elements, P1, P2, and P3. They have local caches, UMA, a symmetric multiprocessor system. The memory is shared. There's a shared address X, and the value of that address is value 1, right? And there's a snoop bus. Messy protocol is a bus snooping protocol. There's a snoop bus. Okay, so let's walk through the example. Now, the first thing that happened was processing element 1 performs a read on that address, and it didn't have, initially it was a miss. So processing element 1's cache controller fetches the value from the memory, right? So at the beginning, when the first time processing element 1's cache controller sees an access to the address X, it was invalid, right? Because it was the first time. Invalid, that block was not in the cache, it was invalid. So when the cache controller sees the state is invalid, it suffers a miss, and first thing it does is it checks in other caches. Is there a cached copy in other caches? So how do you do that? How does the cache controller do that? Place a Snoop read request on the Snoop bus, right? So cache controller of PE1 places a Snoop read request on the Snoop bus, and the others don't have that, so there is no response, right? Or response is negative. So in that case, the cache controller will need to fetch the missing value from the memory. Memory has the up-to-date value. You fetch the missing value, right? So invalid, data block is invalid. Check in other caches, not there, negative response. Fetch the value from the memory. And when the value is fetched from the memory, the state is now transitioning from invalid to exclusive. What does exclusive mean? Only cache copy consistent with memory. Only processing element 1's cache has the cache copy of X, right? X equals 1, and the value is consistent with memory. Other caches do not have a cached copy, right? So the exclusive state is what we have now. After the first read, we have the cached copy marked as exclusive here in this cache. Okay. Now, what happens second? Processing element 3 now is performing a read on the same address, X. Processing element 3 is performing a read on address X. That read comes to this cache controller here of processing element 3. That entry there, once the indexing is done, the state is invalid, right? State in cache 3 here is invalid. State in cache 1 here is exclusive. So PE3's cache controller sees invalid state, right? And what it does is, so it's a miss, it's a cache miss. So what it does is check in other caches. How do you do that? Place a Snoop read request on the Snoop bus, right? Place a Snoop read request on the bus. Processing element 2's cache controller sees that Snoop read, response negative or ignore depending on the implementation. Processing element 1's cache here controller sees the Snoop read request and sees that I have that block cached and it is exclusive, meaning I have the only cached copy, meaning I have the up-to-date value. So I can supply the data from my storage. So for the cache controller of processing element 1, this is a Snoop read hit, right? It's not a CPU memory access hit. It's a Snoop read hit. The memory access, or the Snoop access rather, came from the Snoop bus, and we have a hit for that access. And we can send the data from cache 1 to cache 3, right? Data can be supplied from cache 1 to cache 3. And the state of both blocks, both entries in cache 1 and cache 3 now become shared. Shared, what is the meaning? There are multiple cache copies and the value is consistent with the memory. There are multiple copies of the same address in both these caches, cache 1 and cache 3, and the value is up to date and consistent with the memory. Is it true? Yeah, that is what we are seeing in our example, right? So now both entries are marked as shared. So since there was a Snoop read hit from cache 1, cache 1's cache controller marks its own block as shared, and since cache 1 responded positive to cache 3's controller, cache 3's controller marks that block as shared, right? So note the difference of what happened with cache 1's controller in the previous step, previous memory access. Previous memory access, no other cache controller responded positive. We had to go and fetch from the memory. So the block was marked from invalid to exclusive. For the second access here, cache 3, the block transition from invalid to shared because another cache controller supplied the data, right? Okay, so right, that is the second access. Now we are going to need a write access. PE1, note what happened here. PE1 cache add x equals 1. It's going to write x equals 0, right? That was our example. PE1 is going to write x equals 0. Same address, new value, right? Same address, new value. Block in PE1's cache was shared when that write access happened. Before that write access happened, the state was shared. So to that shared block, cache controller 1 receives a write from the processing element, and it is a hit. We had the data, right? So I'm sorry, there's a mistake. The write is performed by processing element 3, not 1. Processing element 3 performs the write, not 1, right? So both caches had the same shared copy, same value, consistent with memory. Processing element 3 is going to perform x equals 0 write. Okay, so cache 3 controller receives a processor write, CPU write, and that access is a hit. We had the block in the cache. So what do? It's a hit, we update the value. At the same time, we broadcast the invalidate request through the Snoop bus. We receive the CPU write, it's a hit, shared block. We update the block, send a broadcast invalidate signal through the Snoop bus, and change the state from shared to modified, right? Shared to modified. So copy in cache 3 goes from shared to modified with the up-to-date value, and the cache controller there broadcasts an invalidate signal. Note that this invalidation broadcast happens only when a write is received to a shared block. When a CPU write is received to a shared block, the controller needs to broadcast an invalidate signal, right? So an invalidate signal is broadcasted through the Snoop bus. Other cache controllers listening to this Snoop bus see the invalidation signal. So cache 1 had a copy, cache 2 didn't have a copy. Cache 2 just ignores the invalidation signal. Cache 1 sees the invalidation signal, and its state was shared. The block there was shared. So since this is a write invalidate protocol, right, we see the Snoop invalidation, the broadcast signal, and we have a hit. We had a copy. So what we do is cache 1 controller, what it does is it marks the copy as invalid. The copy is transitioning from shared to invalid, right? Processor 3 did a write. Its cached copy went from shared to modified, broadcasted the invalidate signal. Cache 1's copy was changed from shared to invalid, right? Okay. So next what happens is processing element 1 now performs a read, right? Processing element 1 performs a read on the same address. Its block, the copy there is invalid. It's marked as invalid now. There is the tag matches, but the state is invalid. So processing element 1, when it performs a write, there is a tag, matching tag in the cache, but it's invalid. So it becomes a read miss in that cache. Check in other caches. Check, the first thing you need to do is check in other caches whether they have the most recent copy available. So place a snoop read request on the snoop bus. Cache 1 controller places a snoop read request on the snoop bus, and that snoop read request is seen by cache 3 controller. Cache 3 controller had the modified copy, only cache copy, inconsistent with memory, right? So not here. After the previous step, cache 3 had the modified copy, that is the only cache copy inconsistent with memory. The latest update is there, memory has the old value, right? So when cache 3 receives the snoop read request, what it does is there's a snoop read hit, right? It checks its storage there with the snoop address, and it's a hit. We have the most up-to-date value. The state is modified. That means I have the most up-to-date value. Memory doesn't have the most up-to-date value. So what this cache controller does is supply the data, right? Supply the up-to-date data through the snoop bus to cache 1, and then changes the state from modified to shared, because another cache is going to have the same copy now. The change happens from modified to shared. The state goes from modified to shared. Also performs a write back to the memory, because shared state says there are multiple cache copies consistent with the memory. So memory needs to be updated. So when this the latest step happens, processor 3, which had the cache 3, which had the modified copy, writes back to the memory. So memory goes from x equals 1 to x equals 3, now has the up-to-date value consistent with everything, and cache 3 sends the up-to-date data to cache 1, right? So cache 1, which had invalid state, the block was invalid state, it asked other caches through the snoop bus. Cache 3 responded positive with the up-to-date data. So the block in cache 1 now transitions from invalid to shared. Now again, both these caches have the shared block, shared state, x equals 0, consistent value with the memory. Right. I hope that process is clear. Now you can see the coherency among cache data is maintained by the MESI protocol we went through here. It's a write invalidate protocol. When you receive a write, you broadcast an invalidate signal through the system, through the snoop bus, if the block was shared. And other caches containing copies of this block need to invalidate their own copy, right? Okay, so any questions about this? I hope it was clear. Okay. Now we are still talking about this UMA systems, symmetric multiprocessors. Now let's have a look at the scalability. What is scalability actually? Scalability is how can you scale these systems with increasing number of processors? right? So the example we looked at those 3 processors, right? So the same thing can be done with 4 processors, 5 processors, 10 processors, right? 20 processors, and so how the same protocol, same techniques scale with the number of processors, increasing number of processors. One of the biggest problems that we will have with this bus snooping uh, coherency control technique is the contention of the snoop bus as you keep increasing the number of processors. So for 3, 4, 8 processors, smaller number of processors, it's not a big issue. It's not going to slow down the system much when you have a small number of processors like that. But when you have large number of processors, like 30, 40 processors, the contention of the Snoop bus, contention on the Snoop bus and the contention on the memory bus. Now, all these processors might want to access the memory as well, right, at the same time. So mostly on the Snoop bus, but on the memory bus as well. So that contention is going to make the system slow down when you keep increasing the number of processing elements in the system. So it's not going to be very practical for processors for processors containing more than 32 processing elements. It's not a hard threshold, but roughly more than 32 processing elements, then the system is going to suffer more because of the memory contention on Snoop bus. It's not a very scalable technique. So how can you avoid this? How can you avoid this issue and try to increase the number of processing elements in the system? One way you can do this is use alternative approach for buses. Don't use a bus. Use alternative technology like crossbar switches or multi-stage crossbar switch network. So we are not going to go and discuss how a crossbar switch operate, but I strongly encourage you to do a little bit of reading about this. What is a crossbar switch? Just get some overall idea what a crossbar switch is. So um, it's an alternative for a bus-based architecture to connect to multiple, say, segments of memory, banks of memory at the same time, right? So we are not going to discuss the detail, but you can go and have a quick look at it. Crossbar switch, and you can use multiple crossbar switches in a multi-stage network to if you are dealing with a large memory address space distributed over several memory banks, but still accessed in a symmetric manner by a large number of processing elements. So if you use such technologies, you can go up to 256 processing elements in the system, roughly. So that's a large number. It's a significant number. So using multi-stage crossbar switch networks, you can increase the scalability of a symmetric multiprocessor system, a uniform memory access system, using snooping and such snooping techniques and writing validates type protocols. Okay. Right. Now, next thing you're going to talk about is this non-uniform memory access system. Right. So that is designed for even higher scalability. With uniform memory access using crossbar switches and all that, you still have a limit of around 256 processing elements in a processor. If you want to go even more than that, then you have to go for the non-uniform memory access architectures. So it's specifically designed for high scalability. If you want to add thousands of processing elements rather on the same processor, then in such systems, the memory address space is distributed over many devices, separate devices. So not the same memory module, memory address spaces. You still have a single address space from address 0 to address, say, million or something. But the physical locations of those memory addresses are different, right? So address 1 to 10 may be in one device, address 11 to 20 may be different device. That's a very simple example, no? But you get the picture, right? The memory is distributed over different physical memory devices, still having a unified address space. Remember, we are still talking about shared memory multiprocessors, right? The communication happens through shared memory, but the memory perspective of memory for the CPUs or processing elements is not uniform. The processors are going to perceive memory in different ways, right? If you look at this bus, this connection diagram here, you can see that processing element 1's experience of accessing memory 1 is different from processing element 2's experience of accessing memory 1, right? Processing element 1, memory 1 is on the local bus, it's closer, right? So your average access time may be something like 100 clock cycles, right? Like what we discussed in previous topics. But processing element 2, if you want to access the same address in memory 1, you have to go through the system bus, and you have to travel a longer distance and go through system bus and go through the local bus of processing element 1's subsystem to access memory 1, right? So it's going to take a longer time, around 4 or 5 times more clock cycles compared to accessing a local memory, right? Accessing local memory is fast, accessing remote memory is slow. So you have to have some hardware devices called MMU, so memory management units, to synchronize the addresses between addresses coming from these remote processing elements to because the unified address space, same address space, is now distributed across all these memory devices, right? So if you want an example, maybe this memory 1 contains from addresses 0 to 100, let's say, and 101 to 200 are here, 201 to 300 are here. So the entire address space is from address 0 to 300, but it's distributed across 3 memory devices, 3 physical memory devices. So the experience of accessing the same memory location is different to different processors. So it's non-uniform memory access. And what we are looking at here is called NC-NUMA or NC-NUMA. NC stands for non-cached. We don't see any caches here, right? We need to talk about that, but so far we don't see any caches here. Such architectures, there are such architectures without using caches. They are called non-cached, NC-NUMA. So accessing local addresses, local memory, is fast compared to accessing remote memory devices, right? 4 to 500 clock cycles, that is 4 to 5 times more cycles spent on accessing remote memory locations. Then the operating system needs to use special algorithms to relocate blocks for memory optimization. So operating system distributes the workload to these processors, right? So what thread you are going to run, what thread P2 is going to run, what thread P3 is going to run. Remember, these are highly scalable systems. We don't have like 3-4 processors. We have hundreds and thousands of processing elements, and the operating system needs to utilize these processing elements to the maximum, right? So operating system need to balance the workload. So spread out the workload among all these processes as much as possible. So then operating system should relocate blocks from memory for optimization, right? So distribution of the address space among these physical memory locations. Remember, the virtual to physical translation happens through the operating system using page tables and all that. So operating system can use special algorithms to map specific memory, physical memory, to specific virtual memory addresses so that the time spent, overall time spent on memory accesses are optimized across all the processes. Right? So it's a global optimization problem which has to be addressed. So you can't really go and have a pure optimum solution, but you can still optimize and get a better memory access rather than letting the memory be distributed in a fixed manner. Okay. Right. So in contrast to NC NUMA, the other one is CC NUMA, cache coherent NUMA, where you have caches. If you have caches, you have to maintain cache coherency. So such systems will we call cache coherent NUMA systems or CC NUMA systems. So in such systems, bus-based coherence control is not going to work. So we said earlier that bus-based coherence control, snooping, it's not highly scalable. It's practical only up to a limited number of processors, right? 32 processors. If it's bus-based, then you can use other technology to replace buses to increase the scalability, but still limited. So in this CC NUMA system, what we use is called directory-based coherence control mechanism. So it's a different technique to bus snooping, right? So in directory-based coherence control, what we have is something called directory associated with every node in the system, every cache in the system rather. So the directory keeps track of where each block is cached, right? So whenever a processing element wants to access a memory, to maintain cache coherency, the caches should somehow have a way to know whether this block is cached in other places as well. So how the cache controller receives that information is by looking at the directory. You look at the directory to see, okay, do other caches have the same block cache? So directory itself can be distributed like you can see here, right? So the local segment of address space here can be kept in the directory here. So what about the blocks in the address ranges in this memory? If it is there, so if those blocks are cached by other nodes in the system, that is available in this directory. The other address ranges on other nodes are kept in local directories there. The directory itself is distributed. So depending, so the cache controller might need to look at the local directory. If the local directory contains the information about particular block, otherwise it will need to go and look at other directories as well. So if this processing element is accessing a memory address in the range of memory 1, then that details about that memory block will be kept in the local directory. So cache controller can look at that, see if others are having copies of that. If others are having copies of that, you can either invalidate or send updates. So whatever the policy can be decided. But the information is updated and received through directories. So with this, the system bus is going to have more traffic now, trying to access directories to look at directory information. Okay, right. So typically, these directory-based coherence control systems use write-through write policy. Write back it's not practical for these large-scale systems. Okay, so now we talked a lot about shared memory multiprocessors. We talked about uniform memory access. Under uniform memory access, we talked about symmetric multiprocessors, bus snooping, and then we talked about these non-uniform memory accesses. Then directory-based cache coherency control for non-uniform memory access type systems. So all those fall under shared memory multiprocessor. The communication between processing elements happen using shared memory address space, right? So the other type of implementation you can see to facilitate multiprocessor communication is message passing. Communication is done there by messages, passing messages through dedicated channels, not the memory. Memory is now left out. We have dedicated channels to pass data between processors, right? So this is an entirely different programming paradigm. Earlier, it was the very similar programming paradigm to uniprocessor systems, single processor systems, but the hardware and operating system facilitates running multiple programs, threads on multiple processors. Now, this is entirely different. The programmer himself or herself have to do the message passing using the available dedicated channels. Right? So operating system is not going to look after this communication between processors. The programmer has to have a good understanding about the hardware itself, how the messages are passed to these dedicated channels, and then use that information to synchronize between threads or programs. So there is no memory sharing. Processing elements have their own private memories, and because of that, own OS copies, right? Operating system's functionality is limited to the local nodes there. So such systems have architectures like these. They look something like this, right? You can see there's a grid or mesh-like interconnect here, right? You have lines crisscrossing here, and there are some circles connecting these lines here, and they do look like some network routers or something, and in fact, they are something like network routers. So this is actually a network. The interconnect operates as a network, but it's not just a computer network as you see. It's a network on the chip, on the same chip, right? On the same chip, you have hundreds of nodes containing processing elements, caches, and memories. And these nodes connect to routers, and you have a network of routers connecting to each other. And there needs to be some sort of an addressing mechanism in order for processing elements to send messages to other processing elements. So for example, if this processing elements needs to send some message containing data to this other processing element, it will need to place that message on this interconnect through that router by giving the address of the destination processor element. So the message will be transmitted through the network. It might go, the path might depend, some optimal path will be decided by the routing algorithms used in these the little routers here, and the message will be passed to the appropriate destination processing element by the network, right? So you have these mesh grid type interconnects, and they allow really high scalability, right? So contention becomes much less because nobody is accessing shared resources anymore. The bottleneck is removed, right? So the interconnect is now distributed. Routers can make local decisions on which way to pass. Okay, I received a packet or a message from this place, and which direction should I send that message from? And once that is sent, the router is free to attend to other messages coming through the network, right? So the processing of the communication part of the system is distributed through these routers in the internet. But on the other hand, the programmer has a lot of control and also responsibility over interprocessor communication. So if you are writing a program to be run on a processor like this, containing hundreds of processors of processing elements, of course, in such scenarios, you have to be aware of, okay, how the processors are distributed, what is the method of sending data through this network of routers. Those things you have to be aware of, and addressing each processing elements. You have to the program has more control, also more responsibility also. OS is not going to help you much in systems like this. OS is of course going to look after a lot of things in the local node and communication aspects as well. But communication between threads or programs running on these processing elements are mostly handled by the programmer themselves, right? So it's a different programming paradigm compared to the traditional type of multi-threaded programming in traditional shared memory systems that we usually see. The computers we have are multiprocessor systems, and they share memory. They are shared memory multiprocessor systems, and they use all these bus moving type techniques to synchronize or maintain cache coherence. And the programming we don't have to worry a lot about. We can create threads. Operating system is looking after where they are deployed and how the communication happens. But in systems like this, message passing multiprocessors or networks on chip, one of the more common, more up-to-date terms to use for this. There, the programmer has to know a lot about the architecture, and they have to control where the threads are run, how the communication is handled for the most part. So less help from the operating system. So porting or converting traditional programs into such platforms may be difficult, right? Traditional multiprocessor program, multi-threaded programs, if you want to run them on a processor system like this, message passing multiprocessors, you can't just go and run. You have to port them or convert them to the underlying hardware architecture. So that is not straightforward, right? So the programmer has to have a very good understanding about the hardware itself in order to port such traditional applications into architectures like this. So this type of architectures are good for application-specific designs, right? So not for general purpose, but very say known applications. If you're designing a system, the hardware and software both yourself, then you know the application, the type of application you're running on the system as well. So this is a good place for such architecture. So you are the programmer as well as the hardware designer, so you know how the communication happens and this distribution of workload happens. So the development of hardware software can be done at the same time together. Hardware software co-design is the term we use for that. So in such scenarios, application-specific large-scale systems, these message passing multiprocessors are a good choice. Or in the other thing is large systems running several independent tasks. So in the large, say, data center type applications even. So if you want a large number of processing elements without being hampered by the communication interconnect, bus type interconnects, and the tasks run on the system are mostly independent, not sharing a lot of data, then yeah, you can use systems like this. So if you say, you can imagine you have hundreds of processors, you have hundreds of tasks even, a single task may have, say, a small number of threads running on a small number of processing elements. So the communication will happen between those processing elements, and the other processing elements will run other tasks, right? So you have tasks which are independent; they are mutually exclusive. Only the communication happens only within the processing elements used for the task or a given task. Other tasks, communication happen inside that. Between the tasks, there is no communication. So if there are systems like that, so in such scenarios also, this type of large-scale processors are used. And new term that is used to refer to these systems are many core processors, right? Instead of multiprocessors, how to differentiate these large-scale systems, we use a term called many core. You have hundreds and hundreds of cores on the same chip connected by a network like interconnect. Right. Okay. So to summarize, to get the big picture, let's look at something called the Flink's classification. So of parallel processing systems. This is a way a guy named Flink has classified parallel processing systems based on the nature of instructions and data in the system, right? So if you take the first one here, SISD, single instruction, single data. That is what the acronym stands for, single instruction, single data. You have a single instruction stream, a single data stream. So these are traditional single processor systems like the von Neumann architecture or the Harvard architecture even. So the difference is there is the devices for instructions and data may be separate, but still there is only single stream of instructions, that is a single program, and a single stream of data. Data is in the memory, a single memory, and you have to access them sequentially. So single stream of instructions and single stream of data is the traditional single processor system type architecture. Then if you go back to this lower right hand corner, multiple instruction streams and multiple data streams, right? So that is typical multiprocessor and many core system that we were just discussing today. So multiple instruction streams meaning multiple programs, right? Multiple programs may be in the same device or can be distributed across multiple devices. So multiple instruction streams, multiple programs run concurrently using several processing elements, and those processing elements may be using multiple data streams. They need not use the same data stream. They can work on different data, right? So such flexible systems are known as MIMD, multiple instruction, multiple data. So usual multiprocessor systems and many core systems we just discussed fall under this category. So what is SIMD then? Single instruction stream, multiple data streams. Single instruction stream means same program, single program, multiple data stream. So you have a number of processing elements, they run the same program on different data. Such systems are, so these vector processors, GPUs, are falling under this category. They have a large number of processing elements running the same program, same thing is run, same instruction stream is run on all the processing elements, but the data are different. Each processing element work on a different set of data, different subset of data maybe. So these GPUs are SIMD type GPUs employ SIMD type parallel processing method. Then what is left is this lower left hand corner, MISD, multiple instruction streams, single data stream. That is, you have multiple programs, multiple processors working on the same data, which is, you can imagine how the hardware might happen. You have the same memory, same data, but the programs are different. Maybe the instruction memories are different, data memory is same, but it's largely a hypothetical concept. There are no real implementations of MISD. It's just here for the sake of completion, right? We have SISD, SIMD, MIMD, so why not have MISD? And it's just a hypothetical concept. It's not a very practical, useful concept. So that is to give the bigger picture to you. So we have learned about this SISD type systems a lot in the beginning. Then today we talked about MIMD type processor systems. And so that concludes the processor and memory multiprocessor sections of our course here. So okay, so that is it for today, and I'll stop recording.